Talking about quantum, I think. Long title, I'll let you explain it.
Okay. Yeah, well, thanks for coming. So let's see. So I'm going to tell you, specifically I'm going to tell you about an algorithm that solves a particularly a question that's in condensed matter physics. But I understand that that's sort of a kind of problem that people around here are not familiar with or wouldn't necessarily think about it. So it's not really how I'm going to present the talk, and it's not really why I'm giving the talk. And the reason I'm giving the talk is that the kind of question that this sort of answers is the kind of lives in the kind of space that things that are types of problems that are more likely to have been encountered by people in this audience. So so let me tell you what it is that, in general, that this problem is. It's suppose you have an exponentially large matrix that you're given to you in some way that is succinct, so that you it only takes you polynomial time to get the information for this exponentially sized matrix, and you're interested in finding a principal eigenvalue and a principal eigenvector for this matrix. Okay? And I'll even give you something that in hindsight is absolutely necessary, which is I'll give you a guarantee that what you're looking for can be succinctly described. Okay? So you get this sort of exponential size matrix that's given to you succinctly, and a guarantee that the eigenvector that you're looking for, or whatever other property you're looking for, is also succinct. And now the challenge is to do it. So phrased that way, right? It should feel a little more familiar, right? It's sort of there are things in this week that you've seen that it has to do with that, right? So, estimating permanence falls into this sort of framework. Estimating partition functions, Gibbs distributions, Isings and Potts models, they all fall in this picture if you want to put it there. Okay? So my goal is to sort of give you less about the details about the solution details that would pertain to the actual quantum mechanical problem that I'm talking about, and more the sort of the bigger picture feel for what these things are. So all right. So having said that, let me tell you what the actual problem is that we're going to be working on, but don't be too concerned if the details are lost, and there are not going to be that many details. So I just tried to trim it down. So okay. So what's this exponential space that we're going to be thinking of, which has an exponential matrix? It's going to be a tensor product of n copies of some finite small dimensional space. You can think of this as D as 2. Right? So you have this two-dimensional space, you tensor up a bunch of times. Okay? So that's the space on which the operator is going to act on. And let me tell you what the operator is that we're looking for. It's a local Hamiltonian. So what does that mean? There are going to be a bunch of local terms. So HI is going to be considered as like a d squared by d squared matrix. Right? So it's going to act on two copies, which will specify each HI will act on potentially two different copies as a d squared by d squared matrix, and then act trivially on the rest, so tensored with the identity on the rest. Okay, so so each HI is going to be a different one of these matrices somewhere else, and I'm going to add them all up, and that's going to be the big matrix that I'm interested in understanding something about. Okay? So this is called a local Hamiltonian, and typically for physics type things, we think of a little more structure on both this space relative to what these local terms are. So we think of so here the blue dots will represent copies of the three-dimensional space. And a black line will be a particular d squared by d squared matrix. And the black line indicates the two copies of the space that one is interested in. So in the case of a line, these are just nearest neighbor interactions. So the local terms are nearest neighbor, and the lattice, again, nearest neighbors, but on a two-dimensional lattice. So these are the types of things that physicists really do care about.
I'm sorry. So those HIs are not unitary, or are they?
No, they're sorry. So I should have said that. So they're positive norm 1 bounded matrices. So self-adjoint, positive, the spectrum between 0 and 1. Okay. And so what does this have to do with physics? Well, there's a way, there's sort of a model of interactions that sort of say that, hey, a system looks basically like this, at least as an approximation, and that what we were interested in doing is finding out what the low energy or the ground energy, which is the lowest eigenvalue or the near lowest eigenvalues and eigenvectors, what they look like, because the properties of those is going to be helpful for describing what the system is going to do, what the system looks like. Right? So, okay, so that's just sort of your background. But again, just think about it as the framework that I'm going to say is that this is an exponential. This is a matrix in an exponentially large space. We're looking for these low eigenvalue vectors, right? Which is okay. So yeah, and jump in with questions whenever they come to you. Okay, so. All right, so if you adopt this framework that I have to live in this exponentially large space, your first challenge is, look, if I give you a vector in this exponentially large space, it's going to take you exponential time to just look at all of its coefficients, right? So clearly, we're constrained in this way, right? So how do you even do anything, right? Because all these vectors, you can't even describe them, let alone figure out which one it is that you want to be looking for, right? And so, all right, so that's what I've said. Most vectors don't have a succinct description. So here's the big picture intuition to say, hey, I might not have to worry about this as much as it first seems, which is that, the particular problem that we're looking at comes from a physical rendition of a physical kind of thing, and maybe physical states are somehow a little simpler. And so then this image emerges that maybe there's sort of a small corner of this big space, which we can't really work with, but maybe there's a small corner where things can be sort of succinctly described, where the things we're looking for actually are, right? And if that turns out to be the case, well, maybe then this problem is tractable in some way, right? And so, okay, so what is the sort of intuition around what that smaller space should look like? There's a heuristic that basically goes like this, that when we're looking at low energy states, entanglement across from the left part of the system to the right part of the system, and so I know most of you entanglement doesn't mean much, so bear with me for a second, just use it as a word and I'll explain in a second, but that there's some sort of connection between the left side and the right side that should be relatively small compared to a general vector in this space. Okay, so let me tell you what entanglement means. So the mathematical way that I'm going to sort of phrase it is, if I was to describe the state in the tensor product as a sum of component pieces where the component pieces are vectors on the left side tensored with vectors on the right side, the level of entanglement I'm going to measure is how many terms do I have to take. So how many terms of the sum? So generically for a vector, I would have to take an exponential number of terms. But how many terms do I have to take for a particular state? And so we're going to sort of, there's a reason physical intuition says, hey, it shouldn't be that much. Right? The entanglement should be less. And so the number of terms I should be able to take should be less. And let's do something that's reasonably less, like polynomial. Okay, so I'm going to sort of say, let me sort of imagine that the things that I care about have the property that if I cut it in half, and I express things as a tensor product of left halves and right halves, and I sum them up, that I can find some description of those choices of those left and right halves, so that sum is only involves a polynomial number of terms. Okay. And I'm going to say, hey, there's nothing really special about the middle. So I'm going to say, hey, that property is probably going to hold no matter where I cut it, as long as I keep the geometry relative. So as long as I split it left and right, that should be true. Right? So let me hypothesize that those are vectors of interest, right? And let me try to work with those, right?
So are you talking about exact entanglement? So it's exact, right? So not just dropping terms which are small in some norm.
Okay, so we can either talk exact, or we can say, approximately an L2 norm exact, so that there may be a bunch of other terms, but the complete mass of that, Okay, so for people for whom, entanglement, so let me phrase this in terms of probability distributions, which is not an exact correlation, but it should give you the feel for it, right? So you can imagine, suppose I was just dealing with something that is more familiar, which is probability distribution on n-bit strings that you have somehow described, right? And this would sort of, the analogous to this would be somehow that the correlations from left to right are sort of not too much. And what we mean by not too much is that you could describe this probability distribution by first sort of flipping a coin to determine which of some polynomial number of different distributions to search from, which would correspond to one of these B choices. And then you could sample independently from the left side and the right side. So that's the probabilistic analogy to what to meaning of what this.
That B is the rank of a matrix.
What's that? Yes. So that B would be the rank. If you thought of this vector as a map from this space to that space, then it would be the rank of the matrix. And for people who know, I don't know, sorry, the word's escaping me right. The Schmidt decomposition. This is just the sort of number of terms in the Schmidt decomposition. Okay, so again, we're going to sort of say, hey, let's suppose that these are reasonable vectors to think about, and let's concentrate on those. And it turns out that those have a very nice, very, very nice computational way of sort of thinking about them. They're called matrix product states. And this B is termed the bond dimension of them. And I'm not going to say very much about them. And we can talk about them more later. They're a very expressive class of states. I'm going to depict them by a picture like this, right, which is how they are. If for those of you who know tensor networks, this is the tensor network that would describe a matrix product state. And so let me just sort of, just so that you have a picture in mind, each of these ends that are coming down here, you should think of as the component copies of C to the D that we were talking about, right? This green stuff is some sort of information that we gave, that inside of each green dot is going to be some array of numbers, small number of numbers, that's going to be the succinct description. And these lines here are going to encode, remember there was this number B, which was the sum of the number of terms. Somehow that is going to correspond to the thickness of this line. So think of the thickness of this line as how entangled things are, and that together I can give you sort of information. If I give you information about all these green things, that defines a state. And this is called a matrix product state. Okay. So what are the features of this? This is an example of this class of succinctly described vectors that live in our exponentially large space. How much data do I need to give you? The order of n times d times b squared is the amount of data. So it's polynomial in n as long as b is polynomial, and d we were setting to be some small constant. And the key is that we can do linear algebra with these guys. Even though they live in an exponentially large space, we can do things like compute inner products with them. Okay? So if I give you two of these succinctly described things, there are two vectors in this very large space, I can succinctly compute inner products.
You cannot add them, right?
What's that?
You cannot add them.
For a while you can add them. So that when you add them, the bond dimension goes up. So if you want to do a little bit of linear adding, you can, but not too much. Before the bonds get, if you're limiting how much the bond is. Okay, so all right, so now we've got these sort of physically relevant states, and let's go back to this original problem. This was the problem of trying to find these eigenvectors of this particular matrix. And so there were computational there was the history of success on this problem goes back to the 90s with White, who had an algorithm that was heuristic, but that was incredibly effective, very surprisingly so. Right? And it was called the density matrix renormalisation group was sort of the name of the algorithm. It was very successful. It didn't work all the time, but it was very successful, and it was successful in all kinds of places that were pretty surprising, and has been continued to be kind of the go-to way of going about it. And though it wasn't originally thought of this way, in hindsight, here's the way to think about it, which is that we have an ansatz that the the answer we're looking for is one of these matrix product states, right? So this is the this is where we're going to go, and we're going to do variational optimization within that structure. So we're going to sort of take this guy, right, where all these parameters are allowed to vary over everything, and we're going to start marching around varying these parameters, trying to optimize. Okay. So we're kind of bypassing this exponentially large space because we're just sort of variational parameterization on, these are parameters. There no longer is there this linear space in the foreground anymore, and we're just varying along those. Okay, so there were places where this algorithm got stuck and didn't do well, and people sort of wondered, well, this is an assumption. There's an ansatz that the answer should be in this place. So like, how is this a reasonable assumption? So when it works, we say yes, it's a reasonable assumption because we can check that in fact it's a good answer to the question. So, but when it doesn't work, it wasn't sure. So there's a basic question, which was, when it doesn't work, is it hopeless because we're not looking in the right place? And so people started to come up with criteria under which, or sort of musings about criteria that seemed reasonable. And let me just sort of start, I forget the right-hand side of this picture for a second, but let's just look at the left side of the picture. So this is supposed to be a representation of, I'm going to sort of plot the spectrum from 0, for the Hamiltonian, from 0 up to n, which is the biggest it could be if it had n terms. Right? And I'm going to put a little tick mark wherever I see an eigenvalue. Right? And if it's a multiple space, if it's a degeneracy, I'll put many tick marks there. Right? So there is a notion, so again, the spectrum goes from 0 to n. For those people who actually have thought about Hamiltonian, sometimes there's a confusion where people often talk about the normalized Hamiltonian, which is you divide by n, in which case your spectrum should lie between 0 and 1. Okay, but I'm talking about between 0 and n. And I'm going to say, let's look at the cases where there is a constant size gap between the ground state and the second largest state. So the ground state is the lowest eigenvalue and the second lowest eigenvalue. Okay. So let's focus on those guys. All right. So if you normalize the Hamiltonian, then that says that there's a constant over n gap between the bottom one and the second bottom one. And so in that situation, Hastings, and it took until 2007 for somebody to do this, proved that for those Hamiltonians, that in fact this matrix product state guess that there should be, the answer should be describable by a matrix product state with low bond dimension, right? That was done in 2007. And for people, again, who are familiar with these kinds of things, it's a form of what's called an area law, okay? Which goes back to the original picture, which is that these states should have not too much entanglement across from left to right. Right? So one way to think about this is we show that the answer to these problems don't have so much entanglement from left to right. Okay. So then, sort of in this very abbreviated version of the history that doesn't include lots of different things, the next progress was that for these same types of systems, an algorithm was come up that actually showed how to get them. Okay? And that's not the algorithm I'm going to be talking about, but a lot of the ideas that went into that algorithm went into this one too. And after that, there was a second algorithm that was fundamentally sort of in philosophy was different, and that's why I'm talking about this one and not that one. And it's called RRG for Rigorous Renormalisation Group. So renormalization group is a physics idea, and rigorous applies to the fact that this is provable results about them, about how well the algorithm does. And the system, the system for which it says something about is a more general configuration in terms of spectrum. It's the right-hand picture, which is that you've got a ground state, and no longer do you need to have nothing until a constant later. Now, as long as you only have a polynomial of things, number of eigenstates between here and the next, and some constant, then all these states should be describable. All these states we can find them, and they'll all have these matrix product state descriptions too. Okay, and sort of, so this was a proof of in principle an algorithm, and then this algorithm has been the sort of preliminary implementations of it has been doing, and there's I'd sort of say it's promising in terms of being able to answer questions that weren't answered before, and maybe being able to sort of introduce a new set of ideas and that would make things, change things around a bit. Okay, so, right, okay, yeah.
So are you saying that Hastings' construction was not constructive?
Yes. So Hastings didn't say how to find it. It just showed that it had the entanglement properties that you needed to be describable by a matrix space.
Is it true that if you bound the number of summands in your operator, you can bound, maybe by a much bigger bound, the number of summands in that vector that you're looking for?
So is it true?
Well,
yeah.
if you just have one, then I can clearly see that yes. if two, for example.
Yeah, the reason that one can is because it's a problem on a small space.
Right. Even two probably on a small space.
Because it ends up being on a small space. So you kind of would need to cover order n space to be even talking about a problem that lives on an exponentially sized space.
Is there a bound for like one in terms of the other?
You mean non-trivial? I don't think so. No, you can have.
Maybe he's asking even if there's a trivial bound. Like if you just have some terms and you raise it to a power, the bond dimension can be at most.
Are
you talking about operators, or are you talking about the eigenstates of those operators?
So the eigenstates in terms of the operator. So there's probably an exponential bound, right?
But that's just a bound because nothing in the space can have that. Yeah. So there's no a priori. There's no kind of. This is pretty generic in terms of what the ground state can be. But what isn't generic is once you sort of play around with the spectrum. So there are examples where the spectrum is much more concentrated than this, for which the ground state is highly entangled. Oh, and I should have said wave before, which maybe would have helped me not lose some people along the way, that this is the quantum analog of constraint satisfaction. Right? So in constraint satisfaction problems, right, you just sort of say, okay, I've got a few. I'm going to put a local constraint on some number of bits, right? So this would be sort of a constraint satisfaction problem where you were just talking about constraints on nearest neighbors.
Excuse me. Yeah. Well, since you mentioned analog, classical analog, what would be a classical analog of Hastings and your statements? Is there any?
Yeah, I think there isn't, because in the classical case, your solutions are all completely unentangled, right? They're bit strings.
In the classical case, it's sort of trivial. It's like a Gibbs spatial Markov property. So the area law is sort of built into the system. I mean, it says that you condition on the boundary, all these CSTs you have this property that you condition on the boundary of any subset of variables in the constraint graph, then the thing on one side of the boundary becomes independent of the other side. So that's like saying that the perimeter is the area, which is what is non-trivial. I mean, because the non-trivial statement is that the total amount of interaction between the two sides just depends upon the perimeter, which is constant size in the one-dimensional case. And this would be sort of the analog of this would be that there is in the easing model, for example, if you just take 2 points and in a path take 2 points, then the thing inside and outside becomes completely independent.
Well, in classical world, you may consider not nearest neighbor interaction.
No, but this is only for those local interactions. So,
I think more generally in classical, right, when we talk about solutions, we're talking about product states, right? So that, in that sense, because everything's diagonal in the same basis, and so there we wouldn't have entanglement show up. But maybe Okay, so all this is so now let's talk about what this. So I'm going to talk about sort of the ideas that will go into this algorithm. Okay, so I want to just sort of remind you of the original algorithm, which was sort of said, hey, look, let's take this sort of corner of the space that we've identified, and let's do, which is only described by a polynomial number of things, and let's do some variational gradient descent kind of things on that. Okay, so that kind of ignores, to some extent, you could say, ignores the linear algebra structure of this exponentially large space when you're doing that. So let's head towards that exponentially large space just right on. And here's an idea, okay, which I'm sure you've all thought about, right? So let's forget the actual Hamiltonian we're talking about, and let's just say we have a self-adjoint matrix A on some large space, and we want the leading eigenvector. Okay, leading eigenvector. So what do, right? You can start with a random vector, and you can just sort of repeatedly apply the operator, right? And what does that do? It kind of singles out, it sort of suppresses every other vector relative to this largest one, and the amount of that, the speed at which it suppresses this thing is the gap between the largest eigenvalue and the second largest eigenvalue, and all the rest. You know, it suppresses the others even more, right? Okay, so that's the first place where the gap comes in, but it's not the most significant place where the gap comes in. So it's sort of a little bit of a red herring to sort of say, hey, that's why we want gap systems, but sure, it's definitely, if you didn't have a gap system in that sense, you'd run into trouble already here, but that's not the real place. So here's the proposal, right? You start with a random starting vector that let's pick it randomly, but from this nice class, right? We already have a guarantee. Let's suppose we have a guarantee that in the end it's in a nice class, and let's just repeatedly apply A, right? And as we repeatedly apply this matrix A, this vector starts moving along towards there.
It increases this complexity every time, right?
Right. So what's wrong with this picture, right? Or what's going to be hard is, though you started in a nice place and you ended in a nice place, right? The problem is that every time you apply A, you increase the complexity, whatever sort of notion of that is. And so in the middle, you're going to end up with something very highly complex. And there's no guarantee that you won't, and you will. I mean, sort of that's the likely thing. And I've drawn sort of this red thick line to say, just to say that in an exponentially large space, if you sort of pick a random vector, your inner product with the guy that you want to is going to be on the order of 1 over 2 to the n, right? And so for most of the time, and every time, you know, you improve that inner product by a constant every time you apply A, right? But for most of that time, you're sitting way far away, right? And then eventually, by the time you get to 1 over polynomial n angle, then it goes rather quickly. You only need a log number of steps after that. But just sort of pictorially, for a while, you're really, you know, you're not making much progress at all in terms of anything you can see. Okay, so as you pointed out, right, what's the problem with this approach? Well, the problem is that every time you apply A, the complexity or the entanglement sort of doubles or increases by some factor. Right? And so you can't afford, even though it only takes polynomial number of iterations of A to get where you're going, you can't afford that. Right? Your complexity is going to get to be exponential, at which point you can't work with the things anymore. All right. And so again, as what I said before, the beginning is fine, the end is fine, but it's in the middle that's the problem. And so this sort of another way to sort of think about this is, you know, I had this nice picture of this small corner, right? But it's not a corner, right? It's sort of a spread out thing. You're starting out here where it's fine. You're going to end up here where you want to be, right? But your path is going to take you a long way through all these things that you can't deal with. So what do we need to kind of get past this is we need to know how to jump into this process towards the end. If we can jump in, if we can bypass that first part and jump in towards the end, then we're going to be in good shape. We don't have to be that close, but relative to the size of the space, we have to be reasonably close. Okay, so the question is, how are we going to do that? So this is, you know, I've said it, all we have to do is jump in at the end, but that's, I mean, you know, this is a search problem. The whole problem was an exponentially large space. If somebody says, oh, just jump in at the end, I mean, that's where all the problem is. So let me tell you how we do that. Okay, the only thing that we have on our disposal, really, if you think about it, is whatever the nature of the succinct descriptions of the operators and the class of small corners that we're thinking about. That's the only kind of added piece. We know that this thing is going to be impossible if we don't use that. So we're going to have to exploit that. So you should sort of say, the mindset is, hey, we need to exploit something about this fact that everything's been laid out locally in some way. Okay, so so by locally, I mean, that this big exponentially space has been broken up into these tensor products of pieces. Okay, so let me tell you what it is we're going to do. But before I tell you what it is we're going to do, I'm going to, as I was writing this, I was reminded of, it was not a friend of mine, but several friends of mine were present for this conversation with somebody else when they were like in, I think they were like camp counselors, so they were like 17 years old, and they were in some woods, and one of these guys was feverishly looking around and came up with some rock. There was sort of this misshapen rock, and he was feeling very pleased with himself for having this rock, and they asked him, why are you looking for this rock? What are you going to use the rock for? And he said, to build a lathe. And so if people know what a lathe is? This is a mechanical thing. It spins and it's sort of used to shape things, and it's a very precise kind of thing. And so they said, well, what are you going to do with the lathe? And he said, I'm going to use it to build a better lathe. And so they said, well, what are you going to do with that lathe? He's like, well, I'm going to use that lathe to build a better lathe. And they're, what are you going to do with that lathe? And they're like, well, then I would have a really good working lathe. Okay. So, I mean, this is way beyond what I was thinking about when I was 17. But the picture came in mind because we're going to do this in steps. Okay? And in each step, we're going to use the previous step to get ourselves better. And eventually, we'll have something worth dealing with, although at the beginning we don't. And we have to take small steps. So let me tell you what those steps are. So our goal, in the end, is to end up in this exponentially large space with a polynomial size subspace where all the action is. So a polynomial, we're going to try to identify a polynomial size subspace for which the ground states are in there somewhere. And if we can manage to do that, now we're in a sort of regular linear algebra problem in polynomial size space, so that's fine. Okay? So that's our goal. Now, we're starting with an exponentially large space where we know all the action is. And we're going to slowly cut that, each time cutting the exponent, taking the square root of essentially taking the square root of the dimension at each step, refining to a square root of dimensioned space that still has all the action in it. And we're going to keep doing that step by step until we get to one big space that has all the action in it that's only polynomial in size. Okay. So how are we going to do that? All right. So we should think of it. So it's depicted by this picture. So this is the original space. So you should think of each of these as copies of c to the d. Okay. And what we're going to do at each stage is we're going to, using two at a time, we're going to form a subspace of the space spanned by, in this case, for this case, it would be sort of 2 copies of c to the d. By this time, it's 4 copies of c to the d. This time, it's 8 copies, right? So, and each of these squares is going to represent a subspace of the big space that's, the big, increasingly getting bigger spaces. And what are we going to have as a guarantee each time? The guarantee that we're going to have at each time is that the spaces we're keeping around, okay, if we tensor them together, that's a space, that's a subspace of this guy, and that subspace is going to be where the action still is. Okay. So if we can sort of each time keep moving here, keeping the dimension of each of these spaces no bigger than polynomial as we move, by the time we're done, we'll just have one big space. It'll be polynomial dimension with a guarantee that all the action is there, and then we're off to the races.
Invariant respect to Hamiltonian or not necessarily?
No, not necessarily invariant to the Hamiltonian, but in some sense invariant to the low dimensional, the low energy spaces involved.
Also, if the spectral gap is indeed constant, then you need only logarithmically many, right? Iterations, and you don't have to do all these things, right? Or
you mean if the spectral gap is constant?
right.
No, because so spectral gap being constant, there's that.
With respect to n. Okay.
Oh, yeah. So yeah. So that's an important thing to realize, because if otherwise you think this is an easy process. So this is not an easy process even with the gapped. You need to do something like this even for a constant gap, because once you normalize the gap, once we're talking about that matrix A that we were talking about, becomes order 1 over n. And so there you need you need a order n iterations of A to get yourself down to where you need order n log n. Okay, so let me just sort of repeat what I said, right? That we're going to want that the ground state at each level, the things we're constructing, the ground state or the low energy spaces, are very close or lie inside or very close to these subspaces, right? And we also need to make sure that the dimensions of each of these things stay polynomially bounded, of each of the pieces, right? But it's more than they just stay polynomially bounded, because just polynomial bounded, eventually the number of dots inside here, right, is going to be order n, right? At which point, this is going to be a polynomial size subspace of an exponentially large space. So we have to make sure, more than just that we have a polynomial size subspace, we have to know that we can work within that subspace, right? So we need to know that each of these have some sort of matrix product state description that allows us to work in them. All right, so that's the program. That's what we're going to do. All right, what do we have at our disposal to do that? Well, so now I'm going to just describe what are the steps you take to go from, from the one lathe to the slightly better lathe, right? So here's what we do. We start, okay, by doing the obvious thing, which is to tensor the two pieces together, right? So if we have the guarantee that the product of these things by themselves is a good subspace, well, let's just start by tensoring these two things together. We'll still keep invariant the fact that we've kept invariant the fact that their action is all there still. Right? What's the trouble with just saying okay, that's great, let's move on, is that the dimension of this guy has now become the square of the dimension of that guy. Right? But we need to keep the dimensions of these guys polynomial at all times. Right? So we now have this space where all the action is, but it's too big. We can't carry it all around. So we need to make it smaller while keeping all the action in there. Okay. So how do we do that? All right. So it's a two-step process. Okay. The first step is we're going to take a random subspace of this space. Okay. So what does that do? So in terms of goodness, it makes the goodness of the tensor product space very bad, right? So if you sort of said, hey, this whole space is really good at describing what's going on, now I'm going to take a random subspace, it's not going to do very well. But if I just focus on how badly it does within this subspace, it's still not going to do well, but it's only going to do polynomially badly, like 1 over poly badly. Right? So I've taken a random subspace, and whereas before I was doing really well, now the analogy is like my angle, which used to be really close, now my angle is 1 over poly away. Okay? 1 over poly from perpendicular. So which means that only a logarithmic number of iterations would get us back there. If it's an exponentially sized space, this is a problem. But this space that we're dealing with is polynomial. So as a component space, we're far away, but we're polynomially far away. So which implies, at least sort of, if you remember this sort of iteration technique, that if I can find the right operator to point me in the right direction, I should only require to get back to very close either a constant amount or a logarithmic number of applications of something. Right? What that thing is, I'm not quite sure, but something, there's hope that I can get back there. And so that's exactly what I need to do. And the way I do it, because I'm not dealing with the whole space, I'm dealing with a piece of the space, I don't know exactly what operator I'm going to end up applying because I can't figure out what's going on away. But I know the components of the operator that I'm going to apply. And so what I'm going to do is sort of take this space, right, and throw in some operator applied to the space, and throw in some more operators applied to powers of this operator applied to the space. And that way I know that in that span of things I have any operator that would be just a linear combination in some sense of all these different pieces. So again, so what have I done? I've started with a big space. I've taken a random projection to cut it down to a very small space. And then I take the image of that small space under various operators and throw all those pieces together. So now I'm growing the space back up again.
So small means the dimension square root of the product. Or the
Yeah.
dimension, yes.
No, so the random projection is going to be smaller than the square root. But my hope is that when I'm done, because I now grow it again, But when I'm done, I'm getting back to the square root.
So, and if all this works, will you have a like algorithmic proof of Hastings?
Yes. No. Yeah, and you can modify it to be constant.
But do you use that area law?
No. This is the separate.
Essentially, you reprove it. Yes?
Yeah.
Okay.
Yeah. And it's not even, so it is logarithmic in general because a tree, if you go down the worst cut, is logarithmic, but the best cut is constant. So you could reshape the tree. You can show that any, but that's, talk about that. So, okay, so do people sort of basically understand this sort of, I mean, it's very vague. I haven't said what H restricted is. I haven't said, but the idea is, right, you're going to use the fact that cutting down, you're sort of still in a polynomial, this is happening over and over again. You're cutting down individually and you're moving things back individually, and that's going to be enough. Okay. All right. So to make this work so that by the time you've come back to here, two things have to be true, right? One is that using these guys, and that's what the resulting space is, that the tensor product of those things is going to still be where all the action is. Right? That's the first thing it has to be. And this size of the space has to not be too big. That's the second condition that you need. So those two things you need. And so you need, this is the place where the gap condition really comes into play. So what you need, and so let me say, let me tell you very quickly where this H restricted comes from. What's the picture of what it is that you need? And so let me tell you what that is.
I'm sorry, is it clear that you can take random efficiently, or it's not exactly random? So without increasing complexity of the basis and the like. So I mean, do you really mean like random with respect, I don't know, to Haar measure?
Yeah, so let's see, you can orthogonalize things, so you have an orthonormal basis. Now you can.
That doesn't increase complexity as you.
It increases it by a small polynomial factor, but that factor you're sort of including as an overhead, all of which still will not get you back up to the.
Okay.
So each step you have polynomial dimension space and you take polynomial dimensions.
But it's an honest, right? Random subspace, right?
Yeah.
So it's not restricted to any corner of.
No, honest. Yeah, honest.
No.
Yeah. Okay, so the key ingredient to sort of getting this fine analysis to work is a notion of an approximate ground state projection. So what an approximate ground state projection is it's an operator that approximately projects onto the ground state. So let me show you what that means, right? So I'll show it to you in two different ways. So the one way is it's an operator that fixes the ground state and shrinks everything else, right? The perpendicular space every time you apply it, which if you looked at the spectrum would mean where the ground state is, it has an eigenvalue of 1, and everywhere else its eigenvalues lie below delta, between delta and minus delta. So that's the picture of, this would be a delta approximate projection. Okay? But there's the second thing you do is that you're going to apply this projection, right? And so you don't want the complexity to go up too much. So you don't want it to be too, you don't want the entanglement that it adds with each application to be too big. So there's some separate measure of how much entanglement that it adds. And so you're looking for some operator for which, the better you can make delta, the smaller you can make delta is good. The smaller you can make d is good. And the condition that you end up needing, the critical threshold is that d times delta is less than 1. Okay. If you can create a scenario where this approximate ground state projector has this property that its delta and d times d is less than 1, then you get the fact that randomly projecting and reapplying this thing gains you something. Right? And when it gains you something, it means by the time you're back to where you were, you're a smaller dimension than you started with. And that's what you need, because you need to reduce the dimension from something squared back to the something. The construction of this projection, you take the original Hamiltonian, and that's not good. That had a gap, and so you could imagine maybe powers of that, the right power of that could work. But that doesn't work. That gets you right back to where you started from. You need better than that. And the way you get better than that is something that some people may be familiar with, or shouldn't be surprised by, is you end up choosing a Chebyshev polynomial in the Hamiltonian. So
on what interval?
On
From 0 to gap to
No, you end up scaling things down so that all the so that the spectrum is between 0 and 1, and then you do a Chebyshev polynomial on that scaled version. You also, okay, does that make sense?
This is what actually people do in numerical linear algebra.
Mm-hmm.
It's pretty much the same.
Yeah, and that's where, I mean, that's one just borrows tools from that. That's okay. So that's pretty much it. So let me just sort of give you a summary of the pieces, right? So again, this was just to say the thing that I've said a bunch of times, right? The picture is we've got a succinctly described very big matrix of which we're trying to find some principal eigenvector. And so what were the tools? One was, how do we talk about the vectors in that space? That was the matrix product states. And then more in general, tensor networks are a good language for that. They succinctly describe things that express relatively complex vectors. Right? They're very orthogonal. If you're thinking like sparse as another way of identifying a big matrix using just sort of saying, identifying that it's sparse, this is very different from that. These are not, they're completely different. And then we exploited the locality of the problem to sort of build up so that we had a place to jump in. And doing that building up, that sort of modular building up, involved two basic ideas. One was the idea of a random projection. It's because you kind of don't really know where you're going. So the randomness gets you the concentration of getting on average behavior that you want, and then building it back up using an approximate ground state projection, which was what gave you the advantage that you thought you would get from this randomness and the building back up. And then finally, just to remind you, the final step when we get down to the end, right, is a polynomial subspace inside of an exponentially large space. And at that point, since the polynomial subspace is described by matrix product states, you can just do linear algebra there, restrict the Hamiltonian to that space, and then you just write down a polynomial by polynomial matrix that you're trying to solve. That'll give you the coefficients. That'll give you the coefficient, the linear combination of the matrix product states that you had to do that, and that's your answer. All right, and that's it. Thank you.
So if you want to prove again that Hastings using this construction, so do you get a bound? He has this relationship between gap and that B and that measure of entanglement. I assume it's supposed to be part of the result.
You mean the?
So your result, you mentioned his result is if you have gap, you have this simple representation for and is there a bound which connects the measure of entanglement to the gap?
Yes, there is, and I'm trying to remember.
But there is some bound.
There is some bound.
So you recover the same bound.
I think it's a better bound.
You get better bound. Yeah. So but you again, to do all your thing, you need to start with some guys with a priori bound.
You start with a gap.
You start the gap. Gap gives you that those.
Oh, so the bond dimension?
Yes.
Yeah. So the bond dimension ends up.
But you need to start with some bond dimension for your construction.
Yeah. So
what was the initial one?
So it's some function of epsilon, which I've forgotten right this minute.
Of the gap.
Yeah.
Okay.
Of 1 over the gap. Yeah.
And it will get slightly bigger at the end.
No, the whole thing ends up being a bound of. Oh, so you're saying how much do I have to maintain at every step? Yeah, it's polynomial in n and some function of 1 over epsilon.
And what is like the big tool here? So it looks like it's a tricky thing, but rather elementary. Or is there a big tool here?
Big tool?
Yes. Mathematical tool.
I think the mathematical tool is proving the existence of the AGSP. So the thing is, why does the result is why this works, right? I mean, it's that it works. It's a proof that it works, and the fact that it works has to do with the construction of this AGSP and being able to prove that construction has its d and its delta in this proper range. It doesn't add up too much entanglement for the amount of cutting down of the orthogonal space that it gives.
So what is the obstruction if you go to two-dimensional system?
Okay, so that's a good question. So the obstruction is essentially that we can't get an AGSP for that scenario. So there are two obstructions, okay? So the first obstruction is just the problem in itself. You have NP problems in the two-dimensional picture, just classically, right? So you know it's not going to work without something, right? But you could still hope for an area law type, without an algorithm, you could hope for an area law. And for that, so then you would sort of say, okay, can we make this AGSP construction work for that? And let's see, so yeah, so there the problem is, you know, your D, which is the amount of entanglement that you increase. In 2 dimensions, you're sort of dealing with a square. And so you end up with this perimeter of that square coming in as a factor separate from the D. There's a D times this perimeter. And that, you can't, that's just too much to overcome in your delta. You can't rig your delta to be smaller than the amount of entanglement that, at least the ways we've thought about this.
What is that area law?
What does it say? Okay, so the area law in general is something that physicists believe to work in any dimension. But so let me go back to the 2-dimension and 1-dimension picture. All right, yeah. So in 1 dimension, the area law says, hey, the ground state, the lowest energy state, is going to have the property that if I make a cut, the entanglement across the cut should scale by the sort of the quote area that corresponds to the cut. Okay. So in 1 dimension, it scales as a constant, and in 2 dimension, and so I was drawing it as poly n, which is a little bit bigger than a constant, which turns out to correspond to a little bit bigger than a constant, but that's just because the translations of different notions of entanglement. But for 2 dimensions, it would mean that the entanglement in general could be as big as the volume, but physicists expect for the ground state it should be as big as the size of the
square root.
Yeah. So in this case, the square root. Well, yeah, the square root in the exponent.
You don't need it because you prove it, right? So you prove that it works, right?
In this one, yeah.
Oh, only in this one?
Yeah.
What about that one?
Yeah. So that one, there is no known area law, despite the fact that physicists really believe it's true.
Well, I didn't realize. Oh, okay. Oh, I see.
So physicists will say there's an area law.
But the same procedure or rates of the analog will not work here, like merging two things.
Right. So that was sort of akin to the question that someone was asking, which was that in 2 dimensions, the amount of complexity that you add scales, like a perimeter. And that's so it's much bigger. And you can't somehow.
So you wouldn't. So you cannot allow it even to grow, right? So okay. So I see. You have to have the boundary 0-dimensional.
With this restriction, yes, yeah.
Is there kind of a complexity theoretic abstraction? So essentially, here you prove that for certain class of those big matrices, of certain structure, you have polynomial time algorithm. Now you have, let's say, something for another class, and if you can prove that it's a non-approximable or something.
Yeah, so it's unclear whether this. It's unclear whether there are. It's unclear whether this area law holds in more than 1 dimension.
No, but that algebraic equation for matrices which shows up, is there hopelessly to prove that something hard that you cannot approximate those eigenvalues?
Oh, sorry. Okay, so let's make a distinction between an area law type statement, which is a statement that the final solution has a certain form, and then there's a more harder question is, can we find that one? Okay, for the second question, for sure there's an obstruction. There's just classically on 2 dimensions, there's a satisfying, a constraint satisfaction problem. There are plenty that are NP hard.
So which means that you can expect to do this.
You cannot expect to do that.
Yeah. Okay. Yeah. So this is another explanation why bidimensional is handleable and 2-dimensional is not.
That is, but there's the first statement, which is the answer of a certain form. It doesn't cover that, and that is the thing that physicists do believe is true.
Okay, maybe one. Okay, thanks a lot.
Yeah, it's very,